Back, final week, it's gone rapidly. So pretty happy, generally speaking, with your trial exam results. These are probably some of the better results I've seen over compared to previous years. And to think I've said, you know, these guys, they're just not as academic as previous years. No, I've never said that, I'm joking. Okay, so no, pretty happy with your results. And I think perhaps a contributing factor to that is we've done lots of exam questions throughout the year. So we've had plenty of exposure to the types of things they're going to ask. And we had seen some of these questions before, but in conversations with you guys individually, most people said, I remember seeing it before, but I don't remember how to do it. So if I had done it, that was because, I've understood the process, not that I memorized that question. So what we're going to do today, I'm going to have a quick scroll through here of the solutions. There's a couple of questions I want to talk about, but most of them I'm pretty happy with our performance, generally speaking, and then you guys can flick through and see the stuff you didn't quite get right, and then just have a conversation with you guys individually, see how your revision's going, and see what it is you think you need to work on. So we have two booklets. Here is booklet 1. So let's scroll through booklet 1. Now these are my solutions, so they might not be the exact same as the solutions in the revision guide. And even then, the solutions in the revision guide aren't the ones that the SACE examiner uses. These are produced by a separate entity. But it's all correct maths. You might find a few sloppy errors in here, like I tend to make. So first page, I said you should try and not lose any marks on the first page. And generally pretty happy with our performance there. Okay. Moving on to the second page here, I was pretty good with our performance there. So we have calculating probability. This part here, a few people made the mistake of saying it says state one condition that must state one other condition. Okay. So if you read the text above, they tell you the sum of probability has to be 1. Alright, so there's two conditions it needs to satisfy. The sum of probability has to be 1, and the second condition is it needs to be positive. You can't have a negative probability. So that means that's the answer they're looking for there. Some people just wrote the same thing that's listed above. Alright, so that's a problem. Find derivative, that's all fine. Finding the mode, okay? So the mode is the max value. The max occurs when the first derivative is 0. We found the first derivative, and so we're finding the solutions when the first derivative is 0, and we've got the x values there, 1 on top of root 2. We don't consider negative values because we're told the domain here for values of x greater than or equal to 0. Okay, so I'm going to move on. You can come back and have a look at this yourself if you want to. Alright, so we have binomial distribution. Again, pretty happy with our performance here. A number of people made this mistake. We have the probability of x being larger than 80, which means the lower boundary of our binomial calculation needs to be 81. Well, look, I haven't written the answer there, but the lower boundary needs to be 81. Okay, this was good, although it can be a little bit tricky to comprehend what's happening here. And I think a number of people again said that they were sort of read it for a bit and then it clicked. So pretty happy with our answers to B part 1 there. B part 2, all we need to do is calculate E of x. And then in part C, let's talk about the solution to part C. So from this question, right, what it is, it's like a post office, okay? And you go and you pick up your parcel. All right, and they're saying, how long is it going to take for you to get your parcel? And what they're saying is, the robot is generally going to get it in the first, 7 minutes or 12 minutes? 7 minutes? Is that correct?
Yeah.
Yeah, okay. So that's 7, and then and the probability of that happening is 0.9. And then if the robot doesn't get it in 7 minutes, then a human will take a further 12 minutes to get it, and the probability of that is 0.1. And so the problem with this model, all right, is that there's only 2 outcomes. It's either 7 minutes or 12 minutes, or 19, because it's 7 plus 12, so 19. They're the only 2 possible outcomes. Whereas if you think of it, the human might go in there and they're not going to waste 12 minutes, okay, if they find the parcel straight away. They could find the parcel straight away, or it could take them a long time to find it. But there's a whole line of possible values over which they could find it. And so that's why, what's a probability density function? It's a curve where each event occurs over an interval, doesn't it? All right, so that's why this is much better modelled. It doesn't say there's only 2 outcomes. It says there's lots of possible outcomes that could occur. Okay, so that's why it's justified. All right, moving on. Okay, so we've got figure 2 here, finding the slope. Generally pretty happy with that. And then using first principles. Okay, so guys, we know there's going to be a first principles problem. If you find it's something you need to work on, hit me up. I've got so many first principles problems. This should be one that you definitely get right. Okay, because we know it's going to be there. We know what kinds of things they can ask. It's an algorithm. It's just follow the algorithm, get the marks. You know, so there's sort of 5 marks there up for grabs. And you do need to put the x value in. So I thought I'd fix that. But you put the saying find the slope at b. So at point b, the coordinate at b is x is. Where are we told that? At b, what x is 1. So we need to put 1 into the derivative function. Okay, sorry, I did it here. I've done it in this part here, but it should be an arrow pointing up there. So at b, the slope is -4. So let's read this. A student makes the following statement. On the curved function, the slope of chord AB always approaches the slope of the tangent to G when it moves closer. Okay, is this true or not? So what we did over here is we found the slope AB, and what we've done here is we've found the slope at B. All right. So let's consider. I'm going to draw it. So it looks like this, doesn't it? Yep. Okay. And so we've found the slope there as -4. Okay. The slope there is -4. And we also found the slope of this curve from there to there, and we saw that that was -4 as well. Now the claim is, okay, this is the claim. When you move this point closer to here, it gets closer and closer to the slope at that point. All right. So this is evidently not true, because if we move at the moment at this point, it has the same slope as it does at this point. All right. And so if we move this point to here, it's going to be steeper. So just because we move it closer to that point doesn't mean the slope is getting closer. So that's what they're sort of getting at there. If you want me to explain that a little bit more, let me know. Okay, question 5. Now, a little bit, I think this is definitely a question where we should be getting marks, okay? I think the issue that people missed, and maybe if you'd read this just a little bit more carefully, is you would have got the marks here. It says find the exact value. All right, so a lot of people just jump straight to their calculator and smash those numbers. So you're able to sort of get a mark there, but it does say find the exact value. And so what have I done there? I'm saying, well, the y value, we're talking about the y value when x is 1 and when x is 3. All right, so I've put 1 and 3 into the equation there, and the width of both rectangles is 2. And then we're just collecting like terms along there. Okay, so yeah, definitely 3 marks there. I think most of us could get. Maybe we misread the question. Maybe we weren't sure what to do. But yeah, just look out for that. Look out for exact. Okay, now we're told the exact value of the lower estimate, and then we can see, all right, if you have the upper estimate plus the lower estimate, okay, e squared plus e to the -2. Excuse me, sorry, we've got minus e to the -2 and e to the -2. They're going to cancel, and then the same with e squared and e to the minus e to the -2. They will cancel as well. So we're just left with 24. Write an integral expression. Done. And then state a relationship. Okay. Now, I was a little bit generous here, I think. It's only worth 1 mark, but a couple of people wrote 2 relationships. Okay, so they would write D1 equals D4 and D3 equals D2. Okay, so they wrote 2 relationships. It does say state a relationship. So yeah, anyway, most of us were able to see there that the lower estimate and the upper estimate equal. Okay, we have a page of free space. Now, not many people had to use their free space, but if you do, okay, you need to say, let's say you are answering this question, right? Let's say you are answering this question and there wasn't enough room and you wanted to do it on the free page. So you need to say continued on, and you need to say the page that it is on, okay? You need to say continued on, and then this down the bottom here says page 13, all right? So make sure you don't just say, oh, it's written in the extra space, because there's like 4 pages of extra space. Okay, the oyster problem, we have seen that one before. Again, reasonably happy with our performance with this question. I won't dwell on it for too long. And yeah, I'll leave that one. I think you guys can have a look at the solution. We have seen this graphing problem before. It is a tricky one. So I might break this one down again. So I think just continued exposure and keep breaking it down is going to help us with this problem. Okay, we've got figure 6 shows the graphs of f of x and g of x between 0 and 7. For each function has exactly one stationary point. Okay, so if you were to have a look in your calculus book, okay, there are 3 types of stationary points. Okay, we have the turning points. Okay, so this is how it's grouped. All right, stationary points. You have turning points. What's a turning point? That's a max or a min. And the other type of stationary point is a stationary point of inflection. Okay, so we have 3 types of stationary points. We can see on f of x that it's a minimum. We have a local minimum at x is 2, and on g of x it's a point of inflection, that it changes from concave down to concave up. We have a local minimum. Figure 7 shows the sign diagram for the second derivative of g of x. Okay, so what that's telling us, g of x is concave down from 0 to 2. Yep, we can observe that. Look, it's concave down, and then it's concave up until 6. And so there's another point of inflection there. That's what it's telling us. There's another point of inflection at x is 6, because it goes from concave up, and then at 6 it changes to be concave down. State the nature on g of x. That is a stationary point of inflection. Okay, the graph of y equals f of x has one point of inflection at x is 5. Determine the intervals when f dash of x is increasing. Okay, so when f dash of x is increasing. F dash of x is increasing. So let's think about that. Remember, if we have f of x, then f dash of x tells you when f of x is increasing and decreasing. Now we're asked, when is f dash of x increasing and decreasing? Well, that's when f dash dash of x is positive or f dash dash of x is negative. Okay, so let's look at the graph of f of x and draw the sign diagram of f dash dash of x. From here, okay, we can, maybe, are we even given that sign diagram? What are we talking? Okay, the graph has a point of inflection at x is 5. That's the dot that I've put there, okay? And so what you can see is f of x goes from concave up to concave down at x is 5, all right? So if you're to draw the sign diagram of the second derivative, what that means is it is concave up from 0 to 5 and then concave down. This describes when this function is increasing and decreasing. So therefore f dash of x is increasing from 0 to 5 and decreasing from 5 onwards. Okay, that's the link there. Any questions about that? Okay, excellent. So then moving on to over here. Between 0 and 2, tick which statement is true. So let's look at 0 and 2. The first question is about f dash of x versus g dash of x. All right? So let's look at, they're saying the slope. All right? What you can see, we're just looking at the intervals between 0 and 2. So I might sketch that so I can point to it up here on the board. So between 0 and 2, that's f of x. And this is g of x.
Yeah.
Okay. Now the first question we have is about f dash of x and g dash of x. What are they? They're the slope. Okay. What we can see is f of x has negative slope, g of x has positive slope. Okay? Well, that means the slope of this is less than the slope of this. Negative slope, positive slope. So what's the correct box to tick? They don't have the same slope, okay? That the slope of f of x is negative, the slope of g of x is positive, therefore f dash of x is less than g dash of x. Okay, now again, between 0 and 2, which statement is true? We've got, now we're talking about the second derivative, okay? What we can see, concave up, concave down. So that means this function is positive, the second derivative is positive, and here the second derivative is negative. So this one is less than this one. G of x is less than f of x. Okay, and the other way to write that is that f of x is larger than g of x. F of x is positive, g of x is negative, therefore this is larger. All right, between 2 and 7, given that the value of f of x take g of x is increasing, f of x take g of x is increasing, which statement is true? Okay, so let's look back at the graph. What does that mean? Okay, between 2 and 7, what you can see is that the functions are getting further apart. Okay, the functions are getting further apart. All right, as x goes on, they get further and further and further apart. F of x take g of x, that distance increases. So then what do we ask? Between 2 and 7, it increases. Which is appropriate? What this means is this function is steeper than this one. Doesn't it? It has to be steeper if the distance between them is going to increase. And that's why we tick the last box. That over that interval, the slope of f of x is larger than the slope of g of x. Okay? Then sketch the graph of g dash of x. Okay, sketch the graph of the first derivative. So the first thing is we've got g of x, all right? What I'm thinking, g dash of x shows you when it's positive, when it's increasing and when it's decreasing. What we can see is that it's always increasing, right? That along the whole g of x function, it has positive slope, apart from at this point. So it has positive slope, it stops, and then it has positive slope again. So its sign diagram looks like this. Okay, and that point there is x is 2. It's horizontal like that point. All right. The other thing to consider is g dash dash of x. Okay, and we're given this sign diagram. We're given this sign diagram over here. There it is. What does g dash dash of x tell you? They're the points of inflection. Okay, so we have point of inflection. Let's change this to g. We have point of inflection at x is 2 and 6. Sorry, 2 and 6. We have 2 points of inflection. Now, point of inflection on f of x, or g of x in this circumstance, point of inflection corresponds with turning points, which on g dash dash of x are roots. Okay, they're the roots of that sign diagram there. That's the sign diagram of the second derivative. Therefore, they represent turning points on the graph of g dash of x. Okay, so if we have a look at the sketch, we can see what's a turning point. All right, local min. Okay, that it has, it's still above the x-axis, so we still have positive slope, but it touches the x-axis at 2. It maintains positive slope. All right, and then we're told we have, I didn't include this in the sign diagram over here, but we're told we have a point of inflection at x is 6. Okay, so that's here. That's another point of inflection, and the slope changes from positive to negative at that point. Okay, we can see that on the original graph. Concave up, concave down, concave up, and then it changes right here where my mouse is at x is 6, from concave up to concave down. Okay, if you want to talk more about that question, let me know, but I think we've sort of done it to death. All right, our conjecture problem. pretty happy with our performance here. I thought that was pretty good. Most people were able to find the tangent and then observe the pattern. And then a number of us were able to crack it as well, which was great. Because we hadn't seen that one before. That was sort of a surprise. We had seen this problem. It is a hard statistics problem. Now, I'll just talk about that part there. All right, remember that's the kind of language we want to use. The sample is not sufficiently large. So we have two types of distributions we're dealing with. Okay, two types of statistics. We have continuous random variables, all right, or continuous data, it's on a spectrum, and we have discrete random variables. Okay, so they're the titles of our tests. Here's where we did normal distribution. Here's where we did binomial. All right. Here's where we do confidence intervals that have a mean and a standard deviation. Here's where we do confidence intervals that have a value of p. Okay, so that's the sort of difference between. Here, we're obviously talking about a binomial distribution. All right, it's either in the grid or it's not. So, when we're talking about normal distributions, right, n is sufficiently large if it's approximately normal. If it's bell-shaped, we say yes, n is sufficiently large. All right, if it's not bell-shaped, then n is not sufficiently large. When it becomes to binomial, you might remember, n times p has to be greater than or equal to 5. All right, that's the condition it needs to satisfy for n to be sufficiently large. N times p and n times q, sorry, has to be greater than or equal to 5. All right, where q is the inverse probability. So we can bring that up in our notes book if you want to, but that's in there. All right, we have the, here's the confidence interval. Calculate the confidence interval. The lower boundary includes it, so it could be that low. Then that problem there involving the G solving the value of n. We've talked about it before. Let me know if you want to talk about it a bit more. Okay, now this one. A couple of people, I think we should be definitely get part 2 right here. So we've said even if you can get the previous stuff wrong, you can still get some of these later parts of it. So using an algebraic process to determine A. So I just want to talk about the first one, which is the integral of 6x to the power of a half. Okay, so there are two ways of thinking about this. All right. We know a formula for the integral of ax plus b to the power of n. All right, we've got the formula for that written down, so it's just crunching the formula. In this circumstance, b is 0. All right, that's what it is, it's 6x plus 0. Another way you can think about it, and this is using index laws, is if we have a times b to the power of n, that is a to the n, b to the n. So that's probably a better way to think about it, is you have 6 to the half times x to the half, which is just the square root of 6, and that's just a number, all right? So then you're just integrating x to the half, what's that? X to the 3 on 2 on 2 on 3. On 3 on 2 plus 1. What's that? 5 on 2. Yeah. Okay. So that's how you get that part. All right, and then this question we have talked about already. A couple of people missed this. On the axes represent the quantity. So make sure you're reading it carefully, evaluating, and then the integration and the calculus there. So excellent work. I'm going to come around and see how what you guys are up to, how you're feeling, what you're up to, how your revision's going, what you need.
This is possible.